Hello everyone, welcome back to Daikin Cards. So we are finally taking a look at the last problem of the IMO 2025. And while we do have a really difficult yet interesting combinatorics problem. Now this solution has a lot of pretty diagrams, so I cannot wait to show you the solution. Let's get into the problem statement. So the problem statement is as follows. Consider a 2025 by 2025 grid of unit squares. Matilda wishes to place on the grid some rectangular tiles, possibly of different sizes, such that each side of the tile lies on the grid line, and every unit square is covered by at most one tile. Determine the minimum number of tiles Matilda needs to place so that each row and each column of the grid has exactly one unit square that is not covered by any tile. Now I'll go through some examples to help you familiarize with the problem statement, so do not worry. But let's go straight into the exploration phase. I hesitate to call this motivation because it's going to be hard to motivate yourself all the way to the final solution. But nonetheless, I think some exploration will shed some light on the solution. Now, the annoying thing about this problem is that 2025 is a number with many nice properties. One of which is that it is actually a perfect square. So as usual, you might want to start off the problem by trying out small cases. But noticing that 2025 is a square, you might have a suspicion that the solution might make use of this special fact. So meaning to say, the solution might not work for every single size of grid. Therefore, you might be tempted to say, let's start with a 4x4 grid as our smallest case, and you would be very wise to do so. Now, 4x4 grid, you want to have holes such that there's exactly one hole in each row and each column. Obviously, one good way to do that is to put the holes down the diagonal. And then what would be the minimum number of tiles needed to produce this holes configuration? Well, it would be 6. Now, being problem 6, you would suspect that this obvious construction is not going to be the answer. And indeed, you would be motivated to try further to see if you can do better than 6 tiles. One thing you notice is that if you have holes in the middle, it seems to break up potential opportunities to use larger rectangles and therefore smaller number of tiles. Therefore, you might want to try pushing the holes to the edges, which leads you to consider something like this. And voila, you can actually fill up the rest of the grid with 5 rectangles. So you would feel very motivated and happy that, okay, I can get something better than 6. Can we replicate this for a larger grid? Now, unfortunately, the next largest square is 9, so we have to try to do the same on 9x9 grid. Okay, it's not going to be easy or maybe possible to put a gigantic windmill on the whole 9x9. So after playing around a bit, you might instead try and put smaller windmills on the grid instead. And indeed, you can actually put a number of holes following this nice pattern over here, such that you actually get this windmill thing appearing in the middle of the grid. Now these windmill are all of size 3x3, and 3 is the square root of 9, so you seem to be using the property that 9 is a perfect square. This might suggest to you that, okay, maybe we are in the right direction. So indeed, you can fill up the rest of the grid with rectangular tiles like this by basically looking at, for the non-windmill parts, you just use a long rectangle to fill up the remaining squares. Okay, and I will leave you to generalize this construction for a general n square by n square grid. But it's actually very easy to describe. One way to do it is you look at each column, you write down what is the height at which the hole can be found. And in doing so, you can describe the holes to follow this nice pattern by starting with n 2n, 3n, until n square. Then for the next batch, you take one shorter than the previous batch, and so on. And of course, you still need to describe how you would place down the rectangular tiles. But not too difficult, I'll leave you to that task. We now need to calculate the number of rectangular tiles if we were to use this construction. Again, it's not difficult. What you can see is that there will be n-1 square windmills. And for the non-windmill parts, there are basically 4 sections, one for each edge, so to speak. And for each section, you will need n-1 long rectangles. So again, not too difficult to check, so I'll leave you to that. And the number of rectangles will then be n squared plus 2n minus 3. Okay, you have worked quite a bit. You have come up with this non-trivial construction. It's definitely not trivial to even reach this construction. The question is this even a minimum? It will be quite sad if you sweat so much and it's not the minimum. Well, let's now cross our fingers and hope that we can prove that it's the minimum. How might we do that? So one observation is that this arrangement of the holes is actually quite nice. So if you want to come up with a proof, you probably want your proof to be such that this nice arrangement hits the lower bound. If you are someone who is very familiar with the theory of longest increasing subsequence and longest decreasing subsequence, you would probably notice that this pattern is one of the classic patterns that people try and derive in order to concurrently minimize the length of LIS and LDS. And I use this phrase very loosely, but basically, if you look at this sequence of the whole heights, the longest increasing subsequence here is 3. So for example, 3, 6, 9. And the longest decreasing subsequence is of length 3 as well. So for example, 9, 5, 1 is a decreasing subsequence. And it's the longest one of the longest one you can find. So if you look at other permutations of the whole heights, you will get a LIS that is greater than 3 or LDS greater than 3. So there seems to be something about LIS and LDS going on here. That obviously is not an obvious thing to look at, but hopefully it provides some motivation on how to get the proof from the construction. So without further ado, let us jump right into the solution. Now, I need to give a shout out to this AOPS user by the handle of USJL, and the reason is because I'm going to use his key idea in this proof. Reason being that this solution sidesteps the need for an advanced theorem called Dilworth's theorem. I would think most other solutions probably can use Dilworth's theorem to skip one of the steps, but this theorem might not be familiar to some of you. Therefore, I'm going to present this solution that actually only relies on elementary theorems. Now, of course, the logic is still non-trivial. So what we need to show is that for n squared by n squared grid, we need at least n squared plus 2n minus 3 rectangles. The construction I already provided earlier on, I won't talk about it again. Now we just need to show that this is a lower bound. So to start off, we are going to write down the height of the hole from left to right. And we notice that this will be a permutation of 1 to n squared. Therefore, let's say we are given a permutation of 1 to n squared which describes the whole locations. And we want to show that for these whole locations, the minimum number of tiles needed to cover the rest is n squared plus 2n minus 3. Motivated by what we saw earlier in the observation, we will need to look at LIS and LDS. So here are two claims. The first claim is the following. Given a permutation of 1 to k, let A and B be the lengths of the LIS and LDS. Then AB is greater than or equal to k. You will be motivated to look at this if you agree with the observation, because you basically want to show that given your sequence now, your LIS and LDS are somehow bounded by a lower bound, and from there you can hopefully get a lower bound on the number of tiles. Now, proving this claim is actually not difficult. Some might even say this is obvious, and there is a theorem that basically proves this. Nonetheless, the theory might not be familiar to some, so I will go through this claim because the proof is also quite nice. Now, what we do is for the ith element in the sequence, or basically this permutation, we let AI denote the longest increasing subsequence that ends with that ith element. Respectively, Bi will be the longest decreasing subsequence ending with that ith element. So the key observation is that no two elements will have the AI, Bi. No two elements will have the same AI, Bi label. Why is that? It's actually quite easy to see. Suppose I is to the left of J. Now, if sigma I, which is basically the actual value of the ith element, if this actual value is less than the actual value of the jth element, then AI must be less than AJ, because the longest increasing subsequence that ends with this J element is at least taking the longest increasing subsequence that ends with this element and then appending the jth element to it. Therefore, AI is strictly less than AJ. On the other hand, if the value of the ith element is bigger than value of the jth element, then Bi is less than Bj, because the longest decreasing subsequence ending with the jth element is at least as long as taking the longest decreasing subsequence ending at the ith element and then appending the jth element to it. So hopefully this is clear. So we cannot have the same AI, Bi label for every two elements. And since AB is the number of distinct possible labels, your label for AI goes from 1 to A and Bi goes from 1 to B. So AB is the number of distinct possible labels. Therefore, the number of distinct possible labels is greater than or equal to number of elements. AB greater than or equal to K. A very neat proof for this claim. One more thing you can do with that claim is the following. If AB turns out to be equal to K, then it is always possible to choose LIS of length A, LDS of length B such that they share a common element. So this is the key here. If AB equals to K, you can choose your LIS and LDS such that they intersect at a common element. So I'm going to use the same labeling system, the AI, Bi. And since the bound is now type AB equals K, right? So all labels appear exactly once. Now, what we can do then is to consider the elements with label 1, 1, 2, 1, until A, 1. I claim that this is actually a LIS. It's definitely of length A, but we need to show that it's increasing. Well, we do have quite a lot to cover in this proof, and this is relatively straightforward. So I'll leave you to work this, to check this as an exercise. And the hint is basically looking at this diagram over here. And similarly, we can consider elements with the labels 1, 1, 1, 2 until 1b, and this will give you a LDS of length b. And obviously, 1, 1 is the common element that is shared. Okay, so I've shown that it's always possible to do this, and that is what we need for claim 2. Alright, so given the two claims that we have, we apply it back to the main problem. In this case, our permutation of the whole heights, it has length k equals to n squared. So we let the longest length be A, we choose a LIS of length A. We let the longest LDS be length B, and we choose a LDS of length B. And if we are in a scenario where AB equals to n squared, we also impose on ourselves the additional condition that we will choose the LIS and LDS such that they intersect. If AB is bigger than n squared, then we don't need to do this. But if AB equals to n squared, we force ourselves to do this, and we know by claim 2 that it's possible to do so. Now, let us look at the holes on the chosen LIS. Let's say it looks something like this. Now, given that it's a LIS, the little regions that are in between two successive holes on the LIS must not have a hole in them. And this is obvious because if you have a hole in them, you can add that hole and it will make the LIS even longer. So that is then contradicting the definition of LIS. Therefore, each of these shaded regions in between two consecutive LIS holes will not have any holes in them. What this means is that my LIS holes, I'm just going to call them green holes from now on. The green holes, together with these shaded green regions, they split the grid into a up left and down right area. So all the other holes either belong to the up left or down right regions. The green holes themselves lie on the boundary, so to speak. The trick that we are going to do is I'm going to have to label my holes depending on what regions they belong to. So for now, I'm going to assign green arrows to each holes as shown. Basically, if you are in the up left, you get a up and a left green arrow. If you are the down right, you get a down green arrow and a right green arrow. Meanwhile, the green holes will get green arrows in all four directions, up, down, left, and right. You will see why in a couple of seconds. Same thing, we are going to look at the holes on the LDS. I'll call them the red holes. Now, this is just a notation. You could have, in the scenario where the LIS and LDS intersect, then there will be a hole that is both green and red. Okay, so when I say red hole, I don't mean they cannot be green. So we are going to look at the red holes. Same argument, the dotted red regions that are in between two consecutive red holes cannot have any hole in them because that would contradict the maximal length of LDS. Therefore, all the other holes are unambiguously split into upright region or down left region. And I'll label them by giving them red arrows. So I'll assign red arrows. For the upright region, they'll get an up red arrow and a right red arrow. For down left region, they'll get a left red arrow and a down red arrow. Their holes on the boundary will get red arrows in all four directions. And why am I coming up with this weird arrow labeling system? Basically, now I'm going to combine both LS and LDS on the same diagram, and I can now unambiguously label each hole. So specifically for each hole, our shade is up, down, left, or right edge if it has both green and red arrows in that direction. So for example, this hole over here, you look at the green diagonal, it will have been given an up green and a left green. And if you look at the red diagonal, it will have been given a up red and a right red. So only the up direction has both red and green. Therefore, it is unambiguously defined to have to shade its up edge. And you can check that basically what I'm trying to achieve here is that there are four regions, up, down, left, and right. The holes in that region will be shaded on their respective edges. This hole is in the up region, so it is having its up edge shaded. Meanwhile, LIS and LDS holes, they are on the boundary, so we'll shade both. So for example, this hole over here, this green hole, will have its up and right shaded because it is at the boundary of the up and right region. And of course, my arrow notation is just a way to be very precise in defining the regions and what is meant by on the boundary, etc., etc. But intuitively, this is what I'm trying to achieve. So hopefully you understand how the edges are shaded. Now there's one scenario I need to point out, which is that if we have intersecting square, meaning if we have a common square between the LIS and LDS, then that common square will actually have all four of its edges shaded. And you can check that this is basically what follows from the definition of the arrows. Okay, so now that we are all the way here, we might as well take the chance to count the number of shaded edges. And why we want to do that will be clear in a minute, but rather than jumping back to this later, let's count the number of shaded edges while we have the diagrams up here. So starting with the left scenario where the LIS and LDS don't share a common hole, we see the number of shaded edges is, firstly, the number of holes is n squared. All of them have one shaded edge at a minimum, but those on the LIS and those on the LDS have one additional shaded edge. So the number of shaded edges is this, and we know a bound for A and B. The bound appears in the form of the product AB, so we need to apply AMGM to first convert A plus B to greater than or equal to 2 square root AB, and now we can use the bound. The thing is, we know that AB is greater than or equal to K. K is n squared here, let's not forget that. AB greater than or equal to n squared. But whenever AB is equal to n squared, we force ourselves to pick the LIS and LDS to have a common square. So since we are in the scenario where there's no common square, common hole, AB must be at least n squared plus 1. And this plus 1 is very important because that would give us this square root is strictly bigger than n. And since the number of shaded edges is an integer, the next smallest possible is n squared plus 2n plus 1. So this is the lower bound on the number of shaded edges. You see the form n squared and 2n appearing here, so it's looking pretty good. On the other hand, let's look at the scenario where we have one common square. So in this case, we have n squared again. There's n squared holes, all of them have at least one shaded edge. Those on the LIS and LDS that is not the common hole will have one additional shaded edge. So A minus 1 for the green, B minus 1 for the red, and the common square have 3 additional shaded sides. So this simplifies to n squared plus 1 plus AB. Applying AMGM inequality, get 2 square root AB, and AB is greater than or equal to n squared, so we end up with the same bound, n squared plus 2n plus 1. So you see why the common square and this technique of the common square is very important, because you need the plus 1 over here on both sides. Okay, very good. Now we are near the end of the proof. We just need to relate the shaded edges to rectangular tiles in the cover. And this is done through 2 observations. First, each rectangular tile can only touch at most one shaded edge. Now you see where this is going. You're going to bound the number of tiles needed based on the shaded edge. Why is this observation true? Each rectangular tile can only touch at most one shaded edge. Without loss of charity, let's say I'm analyzing the case where the tile is touching the left shaded edge of a whole H. Now firstly, the same column as H have no more holes. So therefore, this right edge of T cannot be touching any more left shaded edge of another hole. Now let's look at the down edge. Can it be touching an up edge of another hole? Well, the down edge of T must lead to the down left of hole H. And since hole H leads to the down left of the red path, it must be the case then that the down edge of T lives in the down left region relative to the LDS. So make sure you understand that reasoning is actually one of the trickier ones. And because of that, notice that all the up shaded edge cannot be inside the down left region because of how I define it. It needs to be in the up left intersect up right regions, right? So therefore, no down edge of T could be in contact with any up shaded edge of another hole. Okay, we have one more chance to revisit this logic. The up edge of T must be to the up and left of hole H. And since hole H must be on the up and left of the LIS, it could be on the boundary, but together that implies that the up edge must be in the up left region relative to the LIS, or it could be on the boundary. But the down shaded edges are all in the down left intersect down right area. So the up edge of T cannot be touching any down shaded edge of another hole. Okay, yes. And then lastly, the left edge one is the most straightforward. It basically leaves towards the left and cannot touch the right shaded edge of another hole. You can check this by using a very similar logic. But in essence, all that is to prove this relatively intuitive statement that the rectangular tile, each of them can only touch at most one shaded edge. And at the same time, observation 2 is that if a shaded edge is not on the edge of the grid, some rectangular tile must be touching it. This one is more obvious. If the shaded edge, like edge of grid is here, right? But if the shaded edge is not on the edge of the grid, then that means there's a unit square next to it where my cursor is, and that square must be covered by a rectangular tile. So a tile must live there and must be touching that edge. Therefore, number of rectangular tiles is greater than or equal to number of touch shaded edges, which is greater than or equal to number of shaded edges minus 4, 1 for each edge. And number of shaded edges is greater than or equal to n squared plus 2n plus 1. And finally, we get n squared plus 2n minus 3. So wow, what a problem 6. It is definitely quite complicated. After we kind of said that problem 3 was too easy, problem 5 is too easy, problem 2 is too easy, problem 6 is out for blood. Well, it's definitely not even easy to come up with the construction, much less the proof. So what do you think of this year's IMO problems? Let me know in the comment section below. And for those of you who took the IMO, I hope you found the experience fun and hope you get the results that you like. Stay tuned to the channel for more math videos, and I will see you in the next one.